Welcome to Beyond Longevity, the podcast that explores not just how we age, but how we can build a longer, healthier future for ourselves. What if some of the biggest diseases of aging are not as different as they appear? Heart disease, kidney disease, and dementia, all associated with what we call aging, affect different parts of the body. But they may share some of the same underlying damage. And if that damage could be stopped early enough, could one treatment do more than tackle a single disease? Could it intervene in the aging process itself? That is the idea behind LinkGevity, a Cambridge biotech company founded by Dr. Carina Kern and her sister Serena Kern-Libera. Dr. Carina is a scientist who studies the biology of aging and is LinkGevity's founder and CEO. Her sister Serena left a senior career in law, government, and financial policy to co-found the company and become its chief operating officer and general counsel. Their starting point is that aging is not one single disease. It is the gradual loss of the body's ability to withstand and repair damage. Over time, that damage appears in different organs and has been classified as aging. LinkGevity focuses its work on necrosis, a destructive form of cell death. When a severely stressed cell ruptures, it can damage the tissue around it and trigger inflammation, scarring, and further cell loss. The company's first potential drug is designed to protect cells before they reach that breaking point. If it works in humans, the same treatment could potentially slow some of the damage that we recognize as aging. It is an ambitious idea, and it has not yet been proven in people, but it has already attracted support from the UK government and interest from the NHS. It has also caught the attention of the UK Space Agency and NASA, because long periods in space place the body under extreme stress and can accelerate some of the biological changes associated with aging. In this conversation, we explore whether medicine has been treating the disease of aging too separately and what LinkGevity's drug is designed to do, why NASA is interested, and whether targeting one damaging process could eventually help us intervene in aging itself. Please enjoy my conversation with Dr. Carina and her sister Serena. Hi, Serena. Hi, Dr. Carina. Thank you so much for joining me on Beyond Longevity today. You are the sisters behind LinkGevity, a biotech company that has a rather ambitious goal. You don't just want to treat the diseases that cause aging. You want to intervene in the biology that is associated with aging. The idea behind LinkGevity is to deal with necrosis, which is a rather violent form of cell death. And it's one of the processes that is associated with aging. Tell us a little bit about why you started LinkGevity and the reason behind it, because I think you, Serena, were a lawyer before you founded LinkGevity. And Dr. Carina, you were always in the field of longevity or science. Tell us how you got there.
Well, first of all, thank you so much for having us on the show. We're both delighted to be here. For us, the company, its foundations stem from a deeply personal experience for both of us. We've always been a very close-knit family. Carina and I grew up in India. And we were very, very close with our grandparents. And unfortunately, we lost them both, and particularly our grandmother, at a relatively early age. And she suffered from quite a sudden downward spiral in her health that the doctors explained away as aging. And Carina always says, when she was young, and when I was young, we would go to the hospital and doctors were able to fix us back up. You go in with a broken leg or whatever it is, they'll give you medication and fix you up and send you back home. But when our grandmother was admitted to hospital, it was a very different approach. They simply said, this is old age. There's nothing we can do here. You just have to come to terms with it. And for Carina, at least, that was what inspired her to go into the field in the first place. For me, if I'm to be honest, why did I agree to come on board LinkGevity? Well, it was FOMO in many ways. A real fear of missing out. I mean, here was an opportunity to really make a meaningful difference to the state of medicine. And I was saying to you earlier, I've just had a little son. To be able to make a change that will influence the next generation, so it's better for the next generation, it was an opportunity too good to miss out on.
You said your grandmother had a rather rapid decline of health. That's not the norm. Normally, the suffering is for years and decades.
Mm-hmm.
So is the idea behind LinkGevity, or your thinking, more to extend lifespan or the health span? Because that's often a sort of, focal point of discussion.
The two go hand in hand. Ultimately, it's these life-limiting diseases limit your life. But what we always say is we're not afraid of dying. And at the end of the day, the reason why we're in this is these are debilitating diseases that rob you of your human dignity. And, you may not be afraid of death, but certainly there's this concern when it comes to these debilitating diseases.
So at what point did this scientific mission that you're on now become LinkGevity? Because I know you, Dr. Carina, were previously at UCL working with C. elegans, which is a tiny little worm and very well known in the longevity research as a whole because its lifespan is rather short and you can see results immediately rather than in other animals like mice that live 3 years or whatever. So tell us a little bit about your early career in research.
Yeah, I always say with that research, for me, it was 3 steps forward, 2 steps back, because the work we were generating, if you like, demonstrated just how different human aging is and how complex human aging is. But also for me, demonstrated a very large gap in general, which is longevity has evolved largely in isolation from medicine. And for me, the company is very much about filling that gap, hence the name, in fact, LinkGevity. It is linking medicine to longevity. And the paradigm, this discovery, everything flows, if you like, from the point of view that we need to take a different lens. We need a bit of a paradigm shift.
It's interesting you ask about the early work, actually, the C. elegans work. For me, at least, watching that early work gave me a hint of what type of a leader Carina might be. And it was really interesting to sit on the sidelines because you sit there and, of course, I will always be the proud sister, even objectively. So for those listeners who don't know this, the C. elegans is a very common model organism that's used in scientific research, as you say. And a lot of work at the time was being put into looking at whether you could switch off single genes in C. elegans, which would cause vast lifespan extension. And the idea was, well, if we throw enough money at this, we'll be able to replicate these effects in human beings. At the time, Carina's work basically said, no, you won't be able to do this. And at the time, I remember people saying around her, if you publish this work, this is going to be career suicide. And Carrie's response was, well, so be it. In science, if you're not courageous and if you're not bold, then it's not going to move the dial. So I think, yes, the work was very different. The early work was very different, but it still gave a hint of, I think, the type of courage which we've applied in LinkGevity, and I think has really borne fruit so far because it is a really new approach to a problem that has obviously existed for many, many, many decades.
And I think it's something really important you mentioned, this fear of career suicide, when all you are is being honest, because that's really what you were. You were saying, look, this is not leading us anywhere. And because, just for the listeners who don't know, and correct me if I'm not explaining that correctly, what you found is that you were able to, I think, extend the lifespan of the C. elegans tenfold. And then obviously you realized that you couldn't replicate that in humans.
Exactly.
Yeah.
The point of the research was yes, a lot of money has been spent on trying to replicate this in human beings. But the point is, you are never going to be able to replicate that same process
It'll
in
never be
human
as
beings.
simple. Exactly. It's not going to be as simple as switching off a single gene and getting this vast extension.
So how did you then move from research at UCL to what you're doing now?
Look, I loved academia, but the other side is I also loved or desired to come up with something tangible. For this paradigm shift, the company just made perfect sense. And we've been very fortunate. We're based at the Babraham Research Campus in Cambridge. So it's this wonderful ecosystem of curated companies mixed in with academia. For me, again, it went back to let's go to the basics. Let's go to the fundamentals. There's been such phenomenal work in the longevity space. Let's build upon it, but most importantly, build upon it where you are spotting the gaps and then bridge those gaps. Now, one of the big gaps I saw, not just in the longevity space, but more in medicine, was the fact that diseases are studied in silos. Open the latest medical textbook or go into the latest hospital. Kidney disease is a separate specialty to cardiovascular disease, to cancer, and so on. And yet, biology just does not work in these silos. We need a systems-level solution for a systems-level problem. How does one develop that? And most importantly, develop that in such a way that you can come out with something tangible to make a shift when it comes to human health span.
You've created a blueprint paper. It's a preprint. It's not peer-reviewed validation. Tell us a little bit about that blueprint paper.
It's a very recent publication, as you say, preprint. And the gist of it is very much how do you take the systems level approach to aging? And to simplify it, the way I look at it is, can you do something akin to factor modeling in finance? Can you identify key nodes driving some of the greatest level of degenerative change across the system and intervene in such nodes so you can have a significant protective effect across the system as a whole? Now, if you look at the paradigm used in pharmacology and drug discovery and development, it has evolved from the idea that medicine had to focus on diseases where there was a single underlying cause, diseases really that were the major burden of the past, such as infectious disease, where there is truly a single underlying cause. Age-related disease is vastly different in two forms, really. One is multiple factors can give rise even to the same disease, or multifactorial. And the second is you see something known as multimorbidity, where multiple diseases are rising simultaneously and they are interacting with one another. And so the idea was taking the standard approach used in drug development, where you're trying to develop a single drug for a single target, for a single disease. It just has not worked. I'm sure this is common knowledge, but just to point it out, this hasn't worked to the point where to date, not a single drug has been approved by any of the major regulators for aging. That's the degree to which this has not worked. And so the point is, how do you come up with this paradigm shift? And again, going back to the factor modeling, if you identify a node, what you will enable is a far more effective approach, yes, for one disease, but more than that, you would have potentially a drug that's able to hit multiple different systems simultaneously.
You've touched upon a few things that I want to delve in a little bit deeper in a moment. But the first thing I want to ask you is, you've said quite correctly that there isn't a single drug for anti-aging or longevity or whatever you want to call it. But is that maybe not because there is no way to test it? I mean, first of all, how do you test it in humans? Because we live so long anyway, that study would have to be over, decades and decades. And also because aging is not really defined as one disease. It's like you said, it's multifactorial. There are hallmarks of aging and all that, but there isn't really a clear-cut definition of what aging is. So isn't that making the whole idea of having a longevity drug rather difficult?
So yes and no, there are elements there which I agree with. let me start with, how do you define aging? And I think the most unhelpful way to define aging is in the abstract. Now, you have to talk about the tangible, degenerative changes you get, right? That's what aging is. And at the end of the day, when it comes to regulators, their indications are based on tangible, degenerative changes. So how would you know if your drug is working or not? Is it alleviating tangible, degenerative change? Yes or no? Whether or not that should be separate indications or one indication, I mean, put it like this, there's nothing stopping you from measuring multiple indications in a clinical trial. Probably you want to start with one, which is a gateway indication, and then from there, widen out. That's our approach. In terms of, is it going to take decades? Not every disease appears at the same rate. Certain organs age faster than others. As one example, one organ particularly susceptible to accelerated aging is the kidney. In fact, this was the reason we decided to pick it as an indication. I think the difficulty is not so much, are we defining it correctly, or is a regulatory landscape in place? It's more as, do you have something that actually works, that you can put through the highest bar of scientific rigor, put it through a clinical trial in humans, and demonstrate that it is having a tangible beneficial effect?
Agree with you 100%. I just want to sort of push you a little bit on that, because if the regulators do not recognize aging as a disease, which isn't in general recognized as a disease, how do you eventually move from approval for kidney disease to approval for aging itself? How do you see that road ahead?
I would flip that and I would say, do you really need, in effect, to have aging as one category? Is it that essential? How essential is it? Because if you get a drug approved for kidney disease, you can now start giving it to patients for kidney disease. Johns Hopkins had quite a nice study there, where by the age of 75, half the population has some form of kidney disease, right? You get it approved for the kidney. You've now got it approved for people to take. But the point is, for me, I think there are two things. One is, yes, of course, it would be helpful. It's not the end of the world if that isn't the case, because I think there's a path one can still take. What I also think, in a way, is it's not on the regulators to change the path. It's on the scientists and the clinicians to change that path. And I think if you manage to prove it in one model, for one disease, you prove not only that you are having a tangible benefit, but that there's a mechanism that can translate, then you're in a much better position to start discussing with the regulators for them to try and change the dialogue. I think it's unhelpful starting the other way around, is all I'm saying.
I think, and maybe that's partly where the blueprint endeavors to start to come in. Because as Carina said, longevity and medicine have kind of developed in two complete silos so far. And medicine has focused on, okay, let's look at the tangible changes, but unfortunately has still stuck with the way in which you look at these diseases as being quite siloed. And the question is, other than this framework, which looks at these diseases in this siloed way, what else is there? And the answer is, well, nothing else is really there at the moment. The other thing is regulators, rightly so, put a lot of emphasis on, well, we need to understand how drugs work. What is the mechanism of action? You can't get away with, and I think, again, very rightly so, you can't get away with saying, okay, well, you take our drug and there'll be some fluffy kind of longevity aging change. I don't think that's what any of us should be pushing for. So I think it's going to be a combination of, let's start the drug discovery approach differently, which is what we've tried to do, which is rather than single drug for single disease, let's start with drugs that actually have system level effects. We like to call them Swiss Army knife type drugs. So it's one drug that actually then applies across multiple diseases. Then you can start having this dialogue of, okay, we're working with biology now. We're understanding that biology is a system. Does the framing, does the narrative, does the categorization then need to change? And that's kind of step 2 of how we get there, I think.
So to me, that sounds very much like what's happening at the moment with the GLP-1s. It was licensed for a particular use, and it is now being used, I don't want to say off-label, but it targets a lot of different physiological systems.
Exactly. I think GLP-1s are an indication of what is possible with a system-level drug. And in fact, the blueprint theory, correct me if I'm wrong, Carrie, predicted early on in the preprint.
There would be drugs with such system-wide effects.
Exactly.
GLP-1s.
And you see now people saying things like, is the GLP-1 actually a longevity drug, quote unquote, right? I think the difficulty, of course, with GLP-1s is people don't understand the mechanism of action. That's the crucial missing link. So the problem is every day they find a new use for it. Every other day they then say that there's this other side effect. But I think that if you look at it in a positive, the positive of this is actually it is possible to have these system-level drugs that hit key nodes. And what you then see is rather than one drug trying to hit one disease that we've kind of pigeonholed this phenotype into calling it is this disease and not this disease, you start looking at a drug that can act across biology.
Which, by the way, I should just add, even for the individual disease, that approach will make it more successful for the individual disease, right? That's the other side of this.
So I'm asking, but I think I know the answer, is do you think we are wrong to treat kidney disease, heart disease, dementia, and other diseases separately if aging is helping to drive all of them?
Well, I think the answer is yes, it's wrong, but at the moment, there's no other way of doing it, right? This is the problem. We are still doing things the way we have done them decades ago when the major diseases at the time had a single cause, which was pathogenic. And where there's a pathogenic cause, yes, there's a single bacterium or a virus, you take that out and you've cured the disease. But biology and the diseases we see now as populations are living longer, this does not work that way. So yes, you can say this is kidney disease, but it's ridiculous almost to say that you can have one disease that's neatly packaged up and doesn't touch the rest of biology. But this is the problem. There is at the moment no other framework and no other way to understand biology and drug discovery. And that's where the blueprint and LinkGevity tries to come in.
What does the blueprint tell us that hallmarks of aging don't?
The hallmarks of aging are incredibly useful. And I always say, it does what it says on the can. They are hallmarks. They are features that you see later in life. It's a typology. And the point is we're still missing information. And again, it's gap spotting. So what does it tell us? It tells us the features that you see. It's not an exclusive list, by the way, of these features. What's missing is A, where do the features come from? B, how do they actually relate to tangible age-related changes? And what type of role do they play? Are they underlying causes? Are they secondary drivers? Or are they symptomatic? So that information is missing. And for me, the benefit of the blueprint, if you try and map, in effect, what the blueprint aims to do is to map the causal chain of events. If you start to do that, then you can put the hallmarks into context and then get a much better understanding of where these tangible changes are actually coming from.
A bit of a provocative question, maybe, but what would need to happen or what would convince you that the whole idea of the blueprint just doesn't work? Just like, you realized with the C. elegans, there was a moment when you just realized, no, this just doesn't translate.
Yeah, look, you have to have, any good theory has what you call risky predictions. You make a prediction, you test the prediction. An early prediction we made is you will see drugs that are able to have effects across more than one system simultaneously. And all of the data from GLP-1 started coming in. Okay, so that's a nice example there. Of course, the other most obvious is if you are talking about these tangible changes, can you actually start to explain where these diseases are coming from? Yes, it does that, right? So that's a big tick. And then the third and the most important for me in terms of a risky prediction is, can you do what no one else has been able to do? Can you develop a drug and get it approved for aging? Can you develop a drug that's going to be key, A, for multifactorial disease and B, for multimorbidity? And at the end of the day, that's why the company was set up, to do some good to improve human health by coming up with such a drug. And of course, I think with the data we're getting and where we're heading with you touched on this, a potential anti-necrotic, a drug to block necrosis, that's such a drug.
Okay, tell us a bit more about this necrosis. So, as I said already, necrosis is a very violent cell death, but you have also apoptosis, which is needed in the body. So, not all cell death, as awful as it sounds, is necessarily bad. So tell us about necrosis and apoptosis and everything related.
So, look, you start with the cell because it's a fundamental building block of all of your biology. And of course, how your cells live, how they die, it determines your health or your lack of it. Now, broadly, there are two buckets of cell death. Beneficial or genetically regulated cell death, right? So these are genes, if you like, that have been conserved and held over the course of evolution because they confer some sort of a benefit. There are multiple types. Mentioned apoptosis, you have necroptosis, ferroptosis, paroptosis, many types. In contrast to all of these, cell death gone wrong. So cell death arising from cellular damage in the absence of any genetic regulation. That is necrosis. Now, necrosis is particularly deleterious when it comes to human health for two reasons. The first is it is the convergence point of a multitude of stresses, intrinsic or extrinsic, right? It's what they land upon to cause death and destruction. But the second key point is necrosis is the amplifier of tissue degeneration. And that goes down to the fact that it is unregulated. So when a cell dies, it's a balloon popping. The cell spews out hazardous intracellular contents into the surrounding tissue. That goes on to trigger unwanted zombie or senescent cells, fibrosis, chronic inflammation, and cascades of further necrosis and damage that then really at the core of both disease onset and progression. Now, necrosis, going back to the factor modeling that I mentioned earlier, if you look at the system, necrosis stands out as a key node. And it's for those two reasons that I mentioned, as well as across diseases, you see the role that it plays. Hence, targeting it is anticipated to have the system-wide protective effect.
How do you know that necrosis is actually driving systemic aging rather than simply happening because other aging processes have already caused the damage?
Look, again, the way I look at it is a keynote. So define driving, right? Because many of the factors that trigger necrosis are also driving. The point is within this network of degenerative change, where there are many factors going in, many factors coming out, can you identify one of the pivotal points of intervention? Think of it like an electric grid that's failing, right? So within the grid, can you identify a key node where if you were to intervene, you would have a protective effect? That's how I see necrosis. Hence, if you are to block it, to give you an example, let's use actual disease examples. Take kidney disease, I've mentioned it. So a multitude of stressors from a lack of oxygen and nutrients termed ischemia, inflammation, oxidative stress, side effects of drugs you may take, nephrotoxic drugs. All of them converge on the same endpoint of necrosis, specifically in the kidney, termed acute tubular necrosis, that then gives rise to this cascade of changes that then gives you both acute kidney injury and chronic kidney disease. You move to the liver, you see a similar pattern. You move to neurodegenerative disease, you see a similar pattern.
You can map out the changes as well, right? So once necrosis sets in, you start to see senescent cell accumulation. You start to see many of the hallmarks of aging itself. So it is, as Carina said, that kind of key intermediate node where if you can block it, then you have the greatest chance of actually materially being able to intervene in something that you were not able to prevent.
But cell death as such is necessary for various sort of processes in the body. How do you make sure you only target the bad cell death, the necrosis, rather than the cell death that is necessary for removing potential cancers or helping skin heal and things like that?
Yeah, that's a great question. Key here is, again, you've got the beneficial or genetically regulated cell death that takes over the processes of removal of cancerous cells. You need it for wound healing, for development. Necrosis is unregulated. It's not there because it confers some sort of an adaptive benefit. It is there because cellular damage results in death of the cell. So I think distinguishing those two are clearly distinguishable. We don't interfere in any of the beneficial genetic pathways associated with programmed cell death. And one of the big benefits for us really in terms of necrosis is you mentioned the role or mapping the role across disease, but also the molecular mechanisms around it. This is a process where the term comes from ancient Greek. That's where we get the word. And the molecular mechanisms, the role in disease, it's been mapped since the 1970s. We know why you get unregulated cell death. The problem actually has been trying to stop it. And the reason for it is not to do with genetic pathways. Upon stress, it's to do with loss of what you call ion gradients. So you have calcium, potassium, various ions, right? And calcium in particular, the concentrations are 10 to 100-fold higher outside the cell than within. And upon stress, calcium floods the cell. Why is this so devastating to the cell? Because it controls multiple cellular processes. And thus, when calcium floods your cell, it switches on multiple cellular processes simultaneously, but in a heightened and destructive manner. What does that do? Well, it then starts to give you, here where many of the hallmarks are going to come in, loss of proteostasis, mitochondrial dysfunction. It's going to give you DNA damage. And of course, either then leave an unhealthy cell living or in extreme circumstances, lead to the death of the cell from the inside out. Then the spewing of contents and everything else I mentioned, triggering fibrosis, senescent cell accumulation, chronic persistent difficult to treat inflammation.
So I'm not a doctor or a scientist, so excuse my next question if it's too sort of basic, but why stop a damaged cell dying rather than prevent the damage in the first place?
So the key is actually not stopping a damaged cell from dying. In fact, switching off programmed cell death would stop a damaged cell from dying. The only way to stop necrosis is to stop the chaotic damage before it arises. And so what you want to do is shield the cell such that you prevent the damage in the first place. You prevent the damage before it leads to those internal negative effects, like your loss of proteostasis, and before it ruptures. And again, the way to do this is to shield against this unwanted calcium entry, which has been termed calcium overload.
Exactly. What we're not doing, put it this way, is taking a damaged cell and then stopping it from dying or bringing it back to life. That's not what we're doing. This is very much acting as a shield to prevent the cell from dying and popping, and then from that further cascade from happening, because that's really where the damage then gets transmitted through the tissue, through the organs, and then you start seeing it more obviously in the biological system.
So now let's go to the heart of it all, LinkGevity's. As you've mentioned, it is designed to prevent calcium flooding into the stressed cells, which is a key mechanism involved in necrotic cell death, as you said. Is it correct that you are combining two existing drugs to do that?
So the biology, the big discovery here was the fact that there were, prior attempts to take out necrosis, and they have been a multitude of prior attempts. They were actually targeting the wrong calcium channels. And there's a vast number of different types of calcium channels within the cell. And key was applying the blueprint theory, the factor modeling, yes, at the macro level, to identify that necrosis is a key node, but then also at the molecular level to identify exactly how to stop calcium overload for the first time. And that told us you actually have to block a subset of channels simultaneously, and only that will give you the protective effect. Biology is pretty simple, actually. If you only block one, calcium can still flood through the other. Hence, you need the subset being inhibited.
What happens to that, let's call it rescued cell afterwards?
So I can only tell you based on observation in the lab, but from observation, it behaves normally. It's shielded. The data is pretty exciting, to say the least. So you can expose cells to harsh hydrogen peroxide, and in the control where you see those cells have died, they're no longer viable, and viable means they're not behaving normally. with the anti-necrotic, they are shielded and they behave normally. And these, this is human cells, human tissue. We've seen this in our preclinical studies as well.
If you look at the experiments that we've done this across a whole range of stressors
And cell types,
which are the quite typical stressors that you would use in a lab. So, for example, the hydrogen peroxide test that Carrie mentioned, we took complex human tissue, exposed it to hydrogen peroxide for 4 hours.
A range of hours,
Yeah, in the sample that did not have the anti-necrotic, the cells were all dead. In the sample that had the anti-necrotic, nothing happened. So to answer your question, what happens when you add the anti-necrotic, the answer is nothing. It looks and behaves normally. You do the same thing with cryopreservation, for example. So you can freeze and rethaw complex human tissue. Again, with the anti-necrotic added to the sample, the cells survive, they behave normally. These are the types of experiments that we've done across a whole range of stressors in the lab. And the in vivo animal data is also looking really positive. Yeah, one of our CROs said that this was pretty unbelievable. They've never seen this in the lab before. Even from a layperson who doesn't really get excited about lab stuff that much. Like, that's pretty impressive.
That's super impressive. And I thank you, first of all, for explaining it to a layperson like me. And it's super impressive. And just to put it in perspective again, because, we have a lot of listeners that are involved in the field of longevity. A lot of them are scientists and researchers, but a lot of them are investors who don't know very much about biology and science. From what I understand, a big problem in organ transplant and growing organs in the lab is that they die of necrosis before they can sort of come to term. So that's quite revolutionary to be able to keep them alive, albeit in a lab. That's already amazing. Tell us a little bit about that.
This is the thing. I think people don't appreciate what a ubiquitous problem necrosis is. It's not just when you talk about disease and inside the human body. That's our focus, that's our main target. But if you look at the reason, for example, that people haven't been able to grow an organ in the lab today, other than skin, you can grow skin because it's really thin. But once you start clustering cells, and if you visualize a ball, once you start clustering the cells in a ball, what happens is the central region gets starved of oxygen and dies, and you get this donut-like structure because of this necrotic core, and the whole structure collapses on itself. So necrosis has been a massive limiting factor in our ability to actually grow anything of a sensible size. And this is where we've actually had people approach us externally with some level of excitement saying, actually, maybe we could apply this here and maybe we could apply it there. But absolutely, it is pretty revolutionary. You say necrosis and then people kind of switch off and it's like, it's boring. But actually, it's until you realize the practical implications and the practical limitations that process places in so many different fields.
I know Link-001 is being expedited to phase 2, but it hasn't obviously been tried in human beings yet. But in the organs that have been lab grown, has it been used yet?
Yes, so the fundamental experiment is something like what Serena was describing, the necrotic cores. You can build these 3D clusters of cells. And again, the central region gets starved of oxygen and nutrients and ends up getting a dead central core. And the challenge is you can't grow your blood system or your vasculature quickly enough before that core forms. And in the lab, we've been able to block those cores completely.
In an actual proper-sized kidney, liver, heart, whatever.
So that's the next stage for us. The next stage actually is finding the right partners. Our primary route is to take this into humans for human medicine. But there's so many other applications. We're actually now speaking with different partners who could take this over and then use it for these other uses.
Oh, that's so exciting. So 2 questions here. When is it being used in lab-grown organs? And when is it going to be used in humans?
I think our focus is to take this into humans. Yes, there's been a lot of interest from third parties, and whether or not we're able to do a deal with the technology with some of these other parties, we'll see. But I think for us, it's really important. And I've spoken with many other startup founders, and they say how important vision is. And absolutely, we realize how important vision is, because you have to stay true to your vision. And we've always said, look, we want to get this drug to improve patients' lives. Yet, how do we do this in the best way possible? And that's how we're kind of structuring our clinical pathway, starting with the kidney as the first indication and then potentially branching out from there. But whether this gets used in the lab reagent sector or the cryopreservation sector, again, of course, all of these would also potentially help move the dial in these areas. Maybe is the answer. It kind of depends on interest and how we react at the time.
So you're looking forward to outsourcing?
Yeah,
certain...
absolutely. We're not going to become an organ preservation company. We can't become a cryopreservation company. We're going to stay focused on the clinical indication. And yeah, we're open to speaking with partners about these other sectors. And we're delighted that there has been this interest. But yeah, as you say, you have to stay focused. And most importantly, you have to stay true to the vision.
You want maximum impact without compromising the ultimate goal, which is improving human health.
So talking about partners, you have a partner that's quite exciting and quite out there, literally. And NASA has been one of your great supporters. You were selected as one of 12 global innovation companies. NASA is super interested in what you're developing. Tell us about this.
I should say this UK Space Agency should be given credit here as well, by the way. Look, space, as you can imagine, as a biotech company, space and astronauts were not the first sector or group of patients that we were aiming for, because otherwise the market would be a really small market. At the moment, anyway, who knows where we'll get to in the next few decades. The reason for the interest is space agencies are starting to think beyond the rockets and satellites and the hardware. And they are starting to think about, okay, well, if we, for example, want to ever be able to get to Mars and man such a mission, how is human biology going to respond, right? In space, and even forgetting about Mars, even, thinking closer to home, space presents a number of different stressors, and these all act to mimic aging or accelerate aging in human beings. This technology, the anti-necrotic, was of real interest because, again, it is a technology that is able to shield your biology from these stressors. So that is the premise from which that interest came. And yeah, it's been delightful to learn about all the different issues that you might experience in space and how space travel might develop in the coming decades. But yeah, I should clarify, that's not our immediate target market.
Have you learned anything from working with space or, space agencies that makes your work on Earth different?
No, I think the big benefit of space is it's just another market. It's another use case where you can apply the same technology, where if you get this approved for humans on Earth, you then can apply it to another population. Yes, one, quite an exciting area indeed. But I think the big benefit for us was the fact that it does not need that much more work. You're not looking at a completely different product.
Exactly. I think that's the key thing. It's the same product, the same technology. It's just another sector that we would never have thought about commercialization in. Like I say, you don't set up a biotech and think, this is something I'm going to, my target market is space. But we didn't realize how much interest there would be. So that has been really fascinating, actually.
But is it not also beneficial to you? Because space ages humans incredibly fast. So is that not a great way of stress testing some of the biology you're studying?
Indeed. And actually, we talked about the kidneys before. Really interesting. One of our collaborators wrote, I think that the paper title is really sexy. It's Cosmic Kidneys. And the question that the paper posed was, would your kidneys survive a trip to Mars? And I think the answer was the kidney would probably be the first organ to fail because it is such a susceptible organ to aging and to stress. And so again, having an anti-necrotic, if we were to try and do a long duration space mission, could become really important.
Now let's come back down to earth a little bit. Is the NHS at all involved in what you're doing?
Yeah, so the NHS innovation arm identified our Lingo 1 as a potential to hit a really high unmet medical need. So even if you just look at kidney disease alone, it is a massive unmet medical need. At the moment, really the only option patients have are dialysis or transplant, and the prognosis on both is not good at all.
And it's very expensive.
It's very expensive. It is a massive burden on NHS resources. So they've identified this as a really interesting, innovative technology. We're working with them. We have a partnership with them. So yeah, so far things are looking positive. But obviously for us, next steps are going to be get regulatory approval. We've had a lot of interest in terms of clinical trial sites to conduct the trial. And then it will be to see what data we get from that trial.
But just to be clear, the NHS is looking at this drug strictly vis-a-vis the kidney rather than longevity or anything else.
They've identified it. It's their innovation arm, and they basically look for innovations that will help move the dial for the NHS. And they've identified, primarily because we would be going in for the clinical trial. For regulatory approval, you have to hook your clinical trial on an indication, and our indication is the kidney.
That being said, one of the things, of course, we'll include in the trial, and they've been excellent about, is how to make sure that it is a gateway clinical trial, because the purpose of the kidney is not to stop at the kidney. It is a starting indication from where you will then springboard into many others, potentially aging itself.
Because I think that's a really important point to make. Everybody that I have on here is really saying politics and insurances and all that. They're not really on the longevity bandwagon for whatever reason, financial. And they all see the benefits, I guess, at some point. But for a lot of the times, it's just not tangible. So that's why I was pushing with the NHS. If they're just looking at it siloed just for the kidney, or if they're sort of open.
I think they see this as a system-level drug. And I think in some ways it's unhelpful to talk about things in terms of longevity, because you're right. Longevity tends to blur into the wellness space, and then people really lose you because then they don't really know what you're talking about. It's not a question of, are we treating debilitating diseases? Are we keeping people in work potentially for longer, healthier? Is this going to improve productivity? And these are the things governments care about. These are the things insurers and financial services firms should care about. Actually, we have a paper coming out on this in the next month or so keep an eye out for that. It's really making exactly your point, which is if we start talking about things in terms of tangible change rather than fluffy kind of longevity terms, then the numbers and the rationale becomes really clear as to why people should care.
Does calling yourself a longevity company make it harder to be taken seriously as a biotech company, do you think?
Okay, I think at the stage we're at, you follow the data, right? As a scientist, you follow the data. As an investor, you should follow the data as well. And I think in our case, the data just speaks for itself.
And I think you need to kind of look beyond the labels, because anybody can label anything, can put any label on anything. Unless you look behind the label and see what it actually is quite tricky. So in some ways, actually, there's a lot of interest in longevity, which is helpful. But like I say, on the other side, sometimes it gets blurred into wellness. And at least for us, given the type of interventions we are coming up with, that's less helpful when we get kind of blurred into that wellness space, I think.
And what do you think is the difference between hype and scientific optimism?
I would just go back to what Carrie said, actually,
Exactly.
Follow the data, because the data should speak for itself. And, the hype is when people just make claims and use adjectives and there's no data backing it up. So for us, it's always been, and this goes right back to Carrie's very, very early days as a young scientist back, even when she was working on C. elegans, she has always been of the view that is her true north. You follow the data. And yeah, I think that's why I'm happy to be on this journey with her and gave up my career to do this, because I believe, you can't argue with that.
It's quite amazing that, you make such a point of it, because one would assume that every scientist would want to follow the data. Obviously, it isn't like that. So interesting. Well, let's leave it at that. Carina,
I'll just say that there are a lot of products out there that you walk into a store sometimes and you think, really, are they really putting this in creams? And, has this really been validated? What is the data to back this up? When you say data, it's two things. One, yes, the results, that's very important. But two, are you going for the highest route of scientific rigor? Are you going into clinical trials? Right? That's the point.
Absolutely. One of my recent guests who developed 2 blockbuster drugs said exactly that, scientific rigor is the foundation of everything. It's just also sometimes quite difficult when you want to bring a product to market to go through the clinical trials. So he himself now has started a supplement company that does follow the same scientific rules and rigors, but obviously you can come to market much quicker. When do you see your drug coming to market?
It's difficult to give an exact date because it's obviously all subject to regulatory approval. But what I will say is, I'll go back to the longevity label here. Many longevity companies will say, decades for their clinical trials. We're not looking at decades. I don't think that's the aim. It's looking at, a handful of years is the hope. But again, I have to caveat that with it's all subject to regulatory approval.
Yes, please, because I'm not getting any younger. Hurry up is what I can say. I think you said that society as a whole is not ready for a major longevity breakthrough. What exactly, do you mean by that?
I mean, just in terms of preparedness, and this is across sectors. Serena was talking about the financial sector. The point is, all that we've built to date has been based on the data we have had to date. We haven't really had a true system-level drug. I mean, a flavor of that is GLP-1s, but a true system-level drug that's able to hit multiple organ systems, multiple diseases simultaneously, and therefore have a vast extension of health span and lifespan, we've never seen it. And so there isn't that preparedness for it. And if you're not prepared, right, a whole range of examples, from governments and retirement ages, insurance companies, pension funds. If you're not prepared, there will be risks. But of course, if you are prepared, in effect, what you have is a potential economic window of opportunity. We've had these in the past, for instance, with the Industrial Revolution. They are good examples. And the point is, if you are able to increase the economically active and you are prepared for that, there's vast potential there for economic growth that could be harnessed.
For sure. I'm a big proponent of that idea. And that's why on the podcast, I have all different kind of people in all different kinds of fields, be it bankers, be it, insurance people, whatever. And the whole idea of this podcast, let's say, is to bring together all these siloed fields of longevity, but also by combining them to make the public aware of it. It is a big, I don't want to say problem, but it's definitely, an issue because, like you said, people will live longer, even without any drug intervention or anything, just the way nature is going. People are living longer. And I agree with you 100% that society as a whole is just not prepared for it, for the normal life extension, let alone with, drugs like yours. That's really crazy. What do you think the longevity field, other than not preparing society as a whole, is getting wrong?
I think we covered it. I mean, the gaps, as I said, there's been such phenomenal work. There are gaps, and how do you fill those gaps? And I think bringing in more of the medical side, for me, that was the major one, which is where the company, what it was really born of at the end of the day.
That's where the name LinkGevity comes from, really. It's linking longevity and medicine. And yeah, I think that has been an issue, which is the siloed way in which these two areas have developed.
Do you think as a whole we understand aging well enough to treat it in its own right?
Again, for me, go back to a complex system, right? Go back to finance and complex systems there. The point is not trying to understand every single element, but the point is trying to identify the key nodes and enough such that you can have protection across the whole and significant. So identify key nodes where you can intervene such that you're protecting as much of the system as possible. I think that's really key. Identifying and then targeting those nodes. And I think the point is, it is very important to have theories. That is an area I've worked in heavily. But at the same time, it is very important to actually try and develop something tangible today. Because at the end of the day, people are dying of debilitating diseases today, not 10 years from today, right?
So your ultimate ambition is to create one treatment that could protect sort of several organs at the same time. Is that?
Look, I follow the data, right? In terms of the anti-necrotic, the predictions, if proven effective in humans, this is what you're going to, anticipate, a protective effect across a multitude of organs simultaneously.
Yeah.
What are you most afraid of getting wrong?
I'm most afraid of losing our vision. And I'll tell you why. When we founded the company, everything that we have done so far, the reason I quit my previous career, right? It's all to realize that vision, which is to help people live more dignified lives, to stop that downward spiral in health, to do something meaningful there. And I think the one thing I would never want to do, and the one thing I would be most afraid of, is if we ended up somehow doing something that went against that vision, because that is the reason I wake up every morning. That is what keeps me going. That is what I want on my deathbed to be my legacy. And, even if we don't come up with the best drug that's able to do the things that we hope it's able to do on my deathbed, I always think about, maybe because I'm such a glass half empty type person, going to say, I'm certainly half empty type person, absolutely. That is the thing. That is the one thing. I don't want to be lying there on my deathbed thinking, I am ashamed of what I've done and I've done something contrary to that vision. Whereas even if I don't succeed, at least I would have tried, right?
And for you?
No, it's the same on your deathbed. What have you achieved, right? Even if you ended up coming up with a great product, if you then withheld that from the people who really needed it, or, didn't use it in the right way, what was the point of anything, right?
Wow, what meaningful words to finish on. I love that. Thank you so much, Dr. Carina and Serena, for coming. You have to come back very soon and update us with what's going on, because it's just so fascinating, and I wish it was faster moving, which is very hard for me.
We have to work with the process.
Try and accept that there's a process to go through and all that, but it just sounds absolutely fascinating. All I can say is hurry up, because as I said, I'm not getting any younger. But yeah, you have to come back. But before I let you go, I have 5 rapid fire questions I ask everyone. What is the single best piece of advice you would give your younger self?
Have courage, because I think doing a startup really does require you to have courage to take that step forward. And looking back, I am really glad to be on this journey. And I would say, to my younger self, have courage. And I'm glad I had the courage to be on this journey.
And you, Dr. Carina?
Say the same. Have courage and follow the data is what I would add to it. So the exact same. And I mean, if you follow the data, then I think the courage just comes inherently.
Spoken like a true scientist, right?
Can't copy all my answers. Make me go first so she can just copy mine.
Name one habit everyone should adopt for a longer, healthier life.
There's only one that actually works, which is lifestyle, to be honest, and things like sunscreen, eating a healthy diet, exercising. There is only one. And I include stress, by the way, mental as well under that.
Yeah, so maybe on the stress point, to live a longer, happier life, did you say, or healthier life? I suppose they come together often.
Longer, healthier.
Yeah. Well, sometimes you're not living longer, it just feels that.
Well, exactly. Yeah, I would say my sister is a scientific expert, so I'd have to take her advice on that one. So it's just, sunscreen.
But it can be anything. You can, read a book, or it doesn't have to be, something.
Have an incredible sister. Maybe have an incredible
I have 2
sister.
brothers.
Get yourself an incredible sister.
And pray. I mean, I start my morning by praying and being grateful for what I have, for my little son. And, that's a really nice, lovely way to start the day and is really relaxing. So, yeah.
That's a good one. If you weren't in the longevity fields, what career would you have chosen? Don't say lawyer, because that.
I did choose to be a lawyer.
Okay, you're off the hook in that one. Fine.
It's an interesting one. This is so much my calling in life. I never chose this because it was a career. I chose this because it's a calling in life. And to be honest, I'm the sort of person where the whole notion of a career is off-putting. So certainly something where I would have been able to contribute to society. So it's this or nothing is what you're saying.
No, I get that. I can accept that. Let's put it this way. What microdose habit, sort of 5-minute routine or small daily action yields outsized longevity benefits?
I mean, it goes back to the lifestyle, right? I mean, the easiest is sunscreen. I would think, plus, of course, again, checking your mental well-being, your physical well-being. But I mean, outside of lifestyle choices, we're yet to have the evidence to demonstrate that anything really works.
Yeah.
What a scientist he is, right? Give us a non-scientific answer.
A non-scientific answer. Honestly, I'm actually just going to say prayer again, because 5 minutes for me can set the tone for the whole day. It can be the difference between having a really stressful, agitated, annoying day versus just feeling grateful and blessed for what I have. And that's just a completely different outlook on the day for me. So yeah, talk about small things with big impact.
For sure. Praying, meditating, whatever you want to call it, just sort of coming to yourself. And the last one, what's the craziest longevity myth you've encountered? And is there any truth to it?
I'm going to refrain.
I'm
going to refrain. That is one I'm just going to refrain from.
Tell us something crazy you've heard, like, drinking your own urine or something crazy like that. You as a scientist must have heard some really funky ideas.
Oh, well, I remember a funny instance where Harry and I walked into a high street store and there was a bottle of snail oil which claimed to have lots of longevity benefits. And Carrie laughs at me and she's like, they just needed to change it to snake oil.
But I mean, look, it's interesting because I think people forget how old the longevity field really is. And you can go back to the father of endocrinology, Charles Sagard. I mean, the talk there was injecting oneself with bull or monkey testes, especially men, for the testosterone, right? And that there's some evidence, of course, especially if it's depleted later in life. Of course, at the time, they then realized the testes don't actually hold enough to have had any sensible effect. The other one's father of immunology, Eli Metchnikov, the whole Yakult, sour yogurt, that's good for you. That comes from him, really, and the fact that Bulgarians, you had some living to their 90s, their 100s. The fact that maybe there's some benefits. And of course, there's a whole gut microbiome, right? So there have been a lot of interesting ideas. It's been the foundation of certain fields. Perhaps we don't often appreciate just how old this topic is. So it's a fascinating area once you get into it.
And it's funny how people they listen sort of with half an ear. They take one little bit and they just run with it. And it's just like, how did you get from, A to wherever you are? Way over there, Yeah. But now you see the women now are injecting spermidine and taking spermidine. So again, going back to, what people kind of knew, I guess often it's also a question of applying or knowing how to apply what you know or what you find. That's often also a problem because we do know a lot of things. We just often don't know.
In the systems lens.
Yeah.
Yes.
Exactly.
Yeah. Anyway, well, as I said, thank you so much for joining me today. It was super fascinating. And
Thank you for having us.
Can't wait to hear where it's going, so keep us updated. Thank you.
Thank you.
Some ideas in medicine are not judged by how compelling they sound, but how well they survive contact with evidence. LinkGevity is asking a bold question. Could one biological process help explain several of the diseases we associate with aging? And if so, could one treatment eventually protect more than one organ in the human body? For now, those questions remain exactly that, questions. The science is very promising, but it still has to withstand the toughest test of all, human clinical trials. What runs consistently through this conversation is Dr. Carina's and her sister Serena's insistence that ambition must be matched by accountability. They repeatedly return to the same guiding principle: follow the data. If the evidence supports the idea, keep going. If it does not, change course. What gives that ambition credibility is the care, scientific rigor, and willingness to follow the evidence behind it. There are still important tests ahead, but the results so far have been very encouraging, and there's every reason to watch what happens next with genuine optimism. I will certainly be following their journey with great interest, and I hope to welcome the sisters back to Beyond Longevity as their drug, LinkGevity's, progresses through clinical development. Thank you so much for joining me on Beyond Longevity today. And please rate, review, and subscribe.